Okay, so we have Anna Duwenig from Universiteit Katholieke Leuven. Probably butchered that, but I tried my best. Who's going to talk to us about smooth Cartan triples and Lie groupoid twists.
Thank you for the introduction. And can people in the back hear me? Okay, good. Just as Chris did, I would like to thank the organizers both of this conference and of the Semitic program because it's been an amazing time here. So thank you very, very much. This work is joined with Aidan Sims. And I'd like to first let you know what I'm going to do. So I'm going to pitch my idea. I'm going to pitch what we worked on and what the idea behind our theorem is. And for that, I also have to talk a little bit about Kumjian-Renaud theory. I'm going to introduce you to Lie groupoids and Lie twists because I don't expect everyone here to be very knowledgeable of differential geometry. And then I'm going to translate what we've done in differential geometry to C*LAT for you. My standing assumptions for this talk, so that I don't have to keep reminding you, I don't have to keep writing it especially, are that E and G are locally compact Hausdorff second countable groupoids. So I'm always assuming Hausdorffness, right? I do want to do manifold theory, so you don't want to throw that out the window really. My G in particular is going to be an étale groupoid. So locally it looks like it's unit space via the range and source map, right? So the range and source maps are local homeomorphisms. And I should say that some results also work for non-étale groupoid, but really that's what we care about. And then eventually there will be a commutative C-star algebra B, and I'll assume that its Gelfand dual is a manifold. And when I write MFD, I mean manifold, and when I say manifold, I mean smooth manifold, right? Not just topological manifold. No boundary. No boundary, exactly. Thank you. Okay, I hope all of that makes sense. So let's start with one. The pitch and Kumjian-Renaud theory. So this has been mentioned in multiple talks by now, which is that we have, on the one hand, groupoid land. Now, on the other hand, we have C** land. And there are some ways to go between them. So if I have a twist over my étale groupoid, oops, and I will define that a little later. So I have a twist. I can build a C* algebra A as the reduced twisted groupoid C* algebra. And this guy has actually a nice subalgebra. I'm in the étale case, so I have functions on the unit space of the twist, which is the same as functions on the unit space of the groupoid. And then the question always arises as in when can I actually go back? Like when can when I have a C* algebra and maybe this additional piece of data, when can I actually construct this groupoid out of it? And so Renaud answered this in 2008. So he says, if G is effective, so if you think of transformation groupoids, think of topologically free actions, then actually this B inside of A is Cartan. So it's a maximal abelian subalgebra with a conditional expectation and it's regular. Don't worry, like you don't have to remember that, but there is a notion. So B has a certain nice property. And in this really nice case where you have a Cartan, you can actually reconstruct the groupoid. And maybe more generally, if I hand you a C* algebra with a Cartan, you can make a groupoid out of it that realizes the C* algebra. Okay? Then there is a result by Kumjian, and I'm slightly redefining history here because Kumjian's result was actually before Renaud's result. So if you assume that G is even principal, then the Cartan has the unique extension property. So in reality, as I mentioned, Kumjian's result was first, and people keep saying that Renaud generalized Kumjian, but that's not quite true, right? Because Kumjian's result says, if you have something stronger here, you get something stronger there, right? Okay, so the Cartan with a unique extension property gives you a principal groupoid. And the question that arose for Aidan and me is, so if you assume G is still effective, so you remain in Renaud's setting, just like Kumjian basically is in Renaud's setting, just a little stronger. So principle, as Robin mentioned, is freeness of the action rather than topological freeness. So your effective plus smooth structure, so whatever that means at this point, can you go back and forth between a Cartan in a C* algebra plus extra data? So this is the question we wanted to answer. If I not only have an effective groupoid in the topological sense, but have more structures, so I have something smooth, I have a differentiable structure, what does that correspond to in C* land? And when I have that stuff in C* land, can I actually go back to get smooth structures over here? Does the question make sense? Cool. Okay. So even though George doesn't seem to be here, I'll start with a theorem in quotation marks at least. So this is our theorem, but I should maybe say the bare bones of it because I'm not going to define anything. I'm just going to say, so suppose, yeah, maybe, okay, I'll say that afterwards. So there is a one-to-one correspondence, which is E, G, twist. Sorry. And actually, I want a lead twist. So I'll define what that means. And this corresponds to B inside of A Cartan plus a set of normalizers that are smooth. And so this triple A, B, and fancy N, these we call Cartan triples, smooth Cartan triples as in my title. So we really found this back and forth street. Okay, and here I should give you the disclaimer. Maybe I should have done that to begin with, which is something that I set up here. I do not try to reinvent Kahn's reconstruction theorem of a manifold. What I mean is, we assume that G naught, which is E naught, which is the same as B hat, when you go between, in these two languages, between these two worlds using Renault, is a manifold. So we take it as a given that you know that this space is a manifold, however you come about it. So it's God-given to you. For example, by Kahn's reconstruction theorem, if you have some commutative C* algebra and some extra function analytic data, you can realize that the Gelfand dual of that C* algebra actually is a manifold. Okay, we just take that for granted. You can do this sort of stuff. Okay, so but now the question is, so how does Renault's two-way straight work? Because if you don't understand how I go between groupoid and Cartan pairs, you won't understand what we've done. So I have to explain at least a little bit how this works. Okay, so the first thing I should maybe do is give you the definition of a twist. So we are now actually in still in part one, Combe-Renault theorem, the second part of part one. So a twist over the état groupoid G is a, again, locally compact Hausdorff groupoid E and continuous open homomorphisms. So I have this sequence, I have my groupoid E, and it projects down to G, but also it includes the trivial circle bundle. So here, this is the unit space of my groupoid. I think sometimes I will drop the, so when I write just G upper 0, I don't mean something open, I mean the unit space, right? This is my notation for the unit space. So I have this short exact sequence of groupoids. And short exact means that my map iota here is a diffeo onto the preimage of the unit space under pi. So this is exactness. And I want that the image of iota is central. Can you bring this up? Okay, so what does this last bit mean, that the image of iota is central? This just means that if I, Come again? Oh, you're right. Thank you very much. You're right. Exactly. Eventually, I want diffeos. Thank you very much. At the moment, the word diffeo does not make sense. I only have topological structures. You're entirely right. Thank you. Bad typo. So I want a homeomorphism onto this image. At the moment, everything is just topological. So iota being central means that if I map an element like this and multiply it by E in E, this better be the same as multiplying on the right by an element like that. Z is in the circle. And so what you get from this is you can define this as giving you an action of the circle on E. Okay, an example for people who haven't worked with twists in Kumjian's sense, this is Kumjian's definition, would be a two-core cycle. So suppose C from the composable pairs of G into the circle is a continuous two-core cycle. Then we let E sub C just be the circle times the groupoid as a set, but we twist its multiplication, so ZG multiplies WH. Wherever G and H are composable in G, I want to define this as, well, in G, I really just do GH. But in the circle, I not just multiply these two numbers, but I also pick up my cocycle. So I have this twisted multiplication. And this guy here is a twist in this more general sense. So here, my inclusion map is literally just the inclusion of the circle times the unit space into this. So I really just include the unit space into G. And my projection map is really just project down to the groupoid. Okay. I should mention, though, that while for groups, these two, at least for discrete groups, but I think something like that should also be true for topological groups, these two things are actually the same notion. For groupoids, they're not. There really are twists that are not coming from two-core cycles. Okay. Now, why do I care about this? Well, as I mentioned here, from such a thing, I can build a C-star algebra. And this was alluded to in Tristan's talk and other talks as well. So we now go from groupoid to C-star algebra, and not in the cocycle setting, but in the general setting where I have my twist. So we have a star algebra. And these are, I denote them CCG semicolon E. And these are all the functions on my groupoid E, which are equivariant with respect to the circle action. And depending on who you ask, sometimes you want conjugate equivariant. You can translate between the two pictures, and for my formulas, this is going to be a little nicer, but it really makes no difference in the end for the C-star algebra. And so this thing, this space here, actually has a nice convolution formula, just like for regular groupoid C-star algebra. Now notice maybe the people that know their groupoid C-star algebras, I haven't assumed that E has a Haar measure. It's a system of Haar measures, or Haar system. It gets that for free. So here I have my groupoid G, which I assume to be étale. Étale groupoids always have a Haar system of counting measures. So there I know what the C-star algebra is. I don't have to assume anything else. But this guy actually inherits a Haar system from that through this very rigid structure that it basically looks like the circle times G. So you can really give this guy a convolution product similar to the convolution product of a normal groupoid C-star algebra. Okay, so we complete that. I'm sweeping lots of things under the rug. But we complete this in some norm, some reduced norm, to get a C-star algebra A. And actually, which is a subvector space of functions. So still of functions defined on E that vanish at infinity and are still Z equivariant. Again, this is something that Tristan mentioned, that there is a sense, so Tristan mentioned this J map of Renault's. You can actually still think of this completion as functions. So this is very, very nice. You can still regard them as that. And as I mentioned here, you have this subalgebra B, which is continuous functions on the unit space. And the unit spaces of these two groupoids actually coincide by exactness. Okay, so this is somewhat straightforward. We know how to make C-star algebras out of initial data. But how do we go back? So from C-star algebra back to groupoids. This is the part that's rather mysterious, I'd say. Okay, so Renault's observation was the following. If G is effective, so again, if you care, this means that the isotropy, and maybe I should say the interior of the isotropy, is actually just the unit space. Then this inclusion of B and A, or maybe I should say differently, how do I want to say this? Yeah, the inclusion of B and A contains all the data for the twist as follows. So the cool thing is that in the effective groupoid setting, so at the moment I'm saying my A really is this C-star algebra, and my B really is this subalgebra. And if I have that, then there is this fact that for an element n in A, n normalizes B if and only if the open support of n, if I project that down into G, so this is a subset of G, this is a bisection. So we have something entirely algebraic that tells us something topological. So what I'm saying here, my n is an element of A. So as I mentioned, you can still think of this as a function. So I can still think of its open support. Here the O actually is an open support. So all the points where it doesn't vanish. At the moment, that's a subset of E. Now project that down to G. And if you get a bisection, meaning one of those sets where my G looks like its unit space, then you normalize the subalgebra. And this is actually an if and only if. That's the interesting bit. Yeah. Oh, thank you. Yes. Thank you. Without that, it doesn't make sense. Just, yeah. You actually want that these two things here land back in B. That's the important bit. Thank you. Okay, so this direction always works. This direction is the one that only works when you are effective. Okay, so let these guys here, I will write them as UN. And these UN are what's crucial. So what happens now is that each such n gives you two things. So the first thing it gives you local homeomorphism from this guy's source to its range. And I'm not saying that this is obvious, but it does, okay? Because of this property. So this property actually gives you this homeomorphism. In Renault's work, these are the alpha n's. But these are really, what these are the maps that say, well, I have my source of this bisection. I can map it uniquely back to this bisection by S UN inverse. And then I bring it down by R to its range. And this is this map, this composition of the source inverse of the source where I can make sense of it, composed with the range. But it gives you one more thing. It gives you a local trivialization. So one thing that the people that have seen twists already might be surprised that there are certain things I'm not assuming, but they actually come for free from these definitions. And one of them is that E actually is a circle bundle. And these normalizers give me the trivialization of that circle bundle. So this means I get maps from the circle times UN. So this is within the circle times all of G, which is homeomorphic to pi inverse of UN inside of E. So you get these local trivializations of E. And what happens is that these maps here, so the first allows you to reconstruct G from its unit space. And the second allows you to reconstruct E from the circle MG. Right? So this is just the idea behind it. So this is why these normalizers are so important, because they allow you to deduce everything from G naught. And remember, G naught is the Gelfand dual of B. Right? Remember that B is defined as the functions on the unit space. So if we know B, we know it's Gelfand dual. So we know this thing. And now the first thing allows us to reconstruct G. The second thing allows us to then reconstruct E. Okay. So that's just the general idea. Are there any questions at this point? Okay, so now we come to part 2, which is Lie groupoids and Lie twists. And honestly, I think I will probably immediately go partially into part 3, but we will see. Okay, so the question that arises here is, can we play that game for smooth structures instead of just topologies? All right, so I would like to do the exact same thing. Like, I would like to be able to reconstruct not only from this guy's smooth structure one on here, and then from this guy's smooth structure one on here. Because remember, the circle has a perfectly fine smooth structure, right? It's a Lie group. Okay, let me make a definition, and I'll probably do that over here. So the first thing that I have to define is what a Lie groupoid is. So what is this word Lie that I keep throwing around? But I'm actually only going to define this in a very specific setting, namely G is an étale Lie groupoid if, so first of all, it's a Lie groupoid. So it's a groupoid. G is a groupoid in the topological sense. And then I also have that G is a manifold. G naught is a submanifold of that manifold. So this means G locally looks like Rn for some n, and G naught locally looks like Rk for some k, smaller than n, within Rn. Then I also want that R and S from G down to the unit space are local diffeomorphisms. So remember, my definition of étale groupoid was R and S are local homeomorphisms. Now I actually want them to be diffeomorphisms. And of course, I just don't want to just have manifold. I actually want everything to be smooth, right? So structure maps are smooth. Okay, why am I giving you the definition only for étale groupoids? The reason is, if you drop the word étal, you can't just drop this definition. You need to assume more. You need to replace this with some definition, because otherwise you want the structure maps to be C infinity, you want them to be smooth, but the composable pairs a priori are not a manifold. They look terrible. So for a Lie group, you're good because the composable pairs are just G times G. If you have one manifold and another manifold, you take the product, you get a manifold. But for composable pairs, it's just this weird closed subset. It's not necessarily a manifold. So you actually need these maps to be submersions, and then it makes sense. But let's just stick to this. Okay. Okay, so an example would be, suppose the integers act on the circle. This time I'm writing it just as S1 rather than T, because this time I don't want to think of this as a Lie group, just as a topological, as a smooth manifold. And I say by rotation, for example, then the transformation groupoid of that action is étal Lie. So it really just inherits the smooth structure of S1. Right? You can play this game more generally. If you have some Lie group acting by diffeomorphism on some manifold, you get a Lie groupoid. And it's étal exactly when this guy here is discrete. Okay? Okay, so now the question that we were after, and at this point, I should apologize to the organizers of the conference. This is the only group action that's going to come up. So, sorry. Okay, so we have this. And then the question is, when we have a groupoid, a topological groupoid, whose unit space is a manifold, can I make a Lie groupoid? And the answer is yes, if. Now this is the proposition that we proved, but this must be known. Like, we haven't found a reference, but this must be known to the groupoid theorists. There's no way that people haven't found this. So suppose G is étal, and suppose G naught is a manifold, then the following are equivalent. There exists a C infinity, so a smooth structure on G, so meaning I can make G a manifold such that G is an étal Lie groupoid. Then this is also equivalent to there exists a unique such structure. And lastly, there exists a topology base UN n in script n of bisections of G such that for all these n's, we have that if I take the source map restricted to one of these bisections, look at its inverse, and compose it with a range map. So this is now a map from S-UN within G naught to R-UN within G naught. Then this is a diffeo. So not just a homeomorphism, but actually a diffeomorphism. So notice here, I'm really just saying something about the unit space. And the idea behind the proof is, well, locally, your G looks like its unit space. So you can use S, for example, to import the smooth structure to G. It's perfectly fine. You can also use R to do that. You always get a manifold. The problem is that composition and inversion on your groupoid might not be smooth unless you have this condition. So these two atlases that you get by importing G naught's atlas to G might differ. And they're exactly the same if you have this condition. Okay? So basically what I'm saying is that similarly to how we think of topological étal groupoids as, well, you just need to know the unit space, then you know the groupoid. Same here. I just need to know the unit space and how it patches together. Then I know the groupoid. Okay, does what I wrote make sense? Or did I again write something where something silly is missing? Does this seem to make sense? Okay, cool. So I'm now gonna move on and translate this condition already into C star land. Let me start this big table. I have time for another 20 minutes, correct? Good, okay. I'll start this big table, which is groupoid land, C star land. Let me just do this. And here I'll have a column that is reason or comment or whatever you want it to be. Okay, so from groupoid land to C star land. I have this condition here. Oh, maybe I should first start with, again, what's my input again? I have E over G twist, just some twist, G effective. So here I have A, the C star algebra of that twist, with B, the C star algebra of the unit space Cartan. This is Renault's theorem, right? Then, oh, I need a tall here again, which was one of my standing assumptions, right? Okay, then I have G naught is a manifold. Again, remember, this is God-given. And here this corresponds to B hat is a manifold. Again, God-given. So this part here is Renault. This part here is God. I don't know what it would be if you're an atheist, maybe con, I don't know. Okay, so we have this. And then comes this condition here. So there exists a topology base, UN, n and script n of G of bisections such that range composed with source restricted to that bisection is diffeal. And here we needed this so that G becomes Lie groupoid. And here on this side, I can already translate this into this language. Having a topological base of bisections tells you there exists a set of normalizers. So these are the normalizers. So all the elements of this form, all the n's that conjugate B back into itself, which densely spans the C star algebra, and then such that. So what does this condition correspond to? That these maps between the unit spaces are diffeos. This corresponds to, okay, remember here, up there, the support of the UNs being bisections corresponded to them conjugating B into itself. Now that there are smooth bisections in a certain sense, this actually corresponds to n conjugating the smooth subalgebra back into itself. So remember, I have a manifold, so B infinity are now all the smooth functions on that manifold. Right? This is my symbol. This was my symbol for that. Does this seem to make sense? Cool. Okay, so now. No, I don't think so. So this corresponds to a certain choice. So if I understand your question correctly. Yes. So now it's true everywhere. You're right. So maybe for the moment, let me say this is a rough dictionary. What was that? Ah. So maybe, and this is, I think, where this question comes from, I forgot to say this, which is that I want that n intersect B is just the smooth functions. Maybe this is answering the question. Maybe this is getting rid of the prosological thing. I think this gets rid of the pathology that you were worried about, right? Okay. Okay, so we have this part of the dictionary, but now I have to move on, right? I have to also talk about twists. And maybe I'll just leave this up here for a moment. And use this. So I was able to do the first for smooth structures. Now I want to do the second from smooth structures. Okay, so I need to make a definition. Oh, there's still some stuff left. So the definition is, and this is a quotation mark because I'm being very vague here, but twist E to G is a lead twist. So, oh, sorry, I should have said this in the beginning. When I just write this, I'm assuming that my iota and everything is also included in this, right? This is abusive notation. So I call this a lead twist if E and G are Lie groupoids. And now this is where I'm saying rough, all maps are smooth. In reality, you just need to assume, very little, and you get that most of the maps are smooth just right away. Like all these, you need to assume that iota is smooth and that pi is a submersion, and then you get, for example, also that these local trivializations of your E, U inverse, UN instead of E, these actually also become smooth. And this is actually also given to you. You need to assume a lot less and get this for free. So these maps that I mentioned that we have up there. And so the hope is now that we can use the fact that these things are smooth to see how you would recover the smooth structure from just the Cartan C star algebra and the normalizers. Okay, so maybe an example first. Again, if C from G2 to the circle is a smooth 2 cocycle, then EC is a lead twist. Remember, EC was the twist I constructed out of a continuous cocycle. So this is a copy of the circle and a copy of the groupoid, sorry. My groupoid, if this is a manifold and I can't talk about a smooth cocycle, and I construct this thing, it has a very clear smooth structure that you should be using, namely the product smooth structure. And this guy actually falls into our definition. So really, our definition is not that out there. So asking that everything's smooth is not that out there. And then the question is, given e.g. a lead twist, what data do we need to reconstruct it from B and A? Okay, that's my question to answer. And now let me see whether I am able to fit this on this board. So I'm playing the same game that I played with Renault's observation, which is saying, okay, suppose you already know that your C-star algebra comes from a groupoid. Suppose it is exactly the groupoid C-star algebra. How do you find the smooth structure in it? That's the question. Okay, so the proposition here is the following. So suppose E to G is a twist, just a topological twist, G étale and effective. So we are in Renault's theorem, in the setting of Renault's theorem. If EG is a lead twist, then there exists a base UN of bisections of G, and there exists for all n, there exists local diffeo, so maybe I should just say local there's this psi alpha, psi n from T un into pi inverse of un smooth such that, so you have smooth trivializations such that you have some properties, namely for all n. First of all, these psi n's, if I look at them only on circle cross the unit space, then I just get the identity. Then for all n mk, I have the following properties. Okay, so these things here are smooth. They're smooth maps from something smooth into part of E. And I'm assuming at the moment that my G and my E are Lie groupoids. So all my structure maps are smooth. Okay, so if I have these nice smooth maps, then I can construct the following maps. So the following partially defined maps from G into E are smooth. First of all, I can map G to some psi n G, but then also some psi m G and take the inverse. I've only concatenated smooth maps, right? My psi was smooth, multiplication in my groupoid E is smooth, inversion in my groupoid E is smooth. It's a smooth map. GH maps to psi n of G, psi m of G, oh, sorry, H, psi k of GH inverse. Same game. Multiplication in my groupoid G is smooth, multiplication with these psi n's are smooth, multiplication in E is smooth, inversion is smooth. This is a smooth map, just composed smooth things. And lastly, G maps to psi n of G, psi m of G inverse. Again, everything's smooth, this is smooth. Now you would wonder, why do I care about these? Why do I care about these maps? Why have I looked at these? The cool thing is that you can go back. So here my proposition earlier, I said, suppose you have a Lie twist, then you have this stuff. But now, I'm erasing that. I'm saying, if you have a base of bisections and continuous local trivializations, such that, okay, at the moment, I have a map from G to E. Well, E, I'm trying to construct a smooth structure on E. So look here, my G inverse, this actually lands in pi inverse of G naught. So I can, in reality, move this back via the iota map to the circle cross G naught. And I can do the same for all of these. All of these, I have a G and a G inverse coming up, so in reality, they lie in the image of iota. I have a G and H coming up and a GH inverse coming up, so I land in the image of iota. So now I have maps from G to the circle times G naught. And if I let this here be a Lie groupoid, so G is a Lie groupoid, not E, then if I have this, there exists a unique smooth structure so that E is a Lie groupoid, and we have a twist. So then E to G Lie twist. So I have rephrased the properties that a Lie twist gave me entirely in terms of G and G naught. So if G is a Lie groupoid and I have this stuff, I can actually patch them back together to give me a smooth structure on E. Let me call this property here is U infinity. U infinity just says don't mess with the smooth structure on the circle. This is S infinity, which says the sections that I picked up here are compatible with one another. This one here, M infinity, tells you that the multiplication of E is smooth. And this one here, I infinity, tells you that the inversion is smooth. And now I can go back to my table. The inverse is inside or outside. Very subtle, and I always trip over that too. Yes, I think you do. So what now happens is that if you have u infinity and s infinity, this tells you that E is smooth bundle, so a smooth principal bundle. If you also have M infinity and I infinity, then this tells you that E is B-twist. And now I just have to translate into here. And it will look similar to this, just a little more messy. So I have my psi n's. So I've given them the psi n for a reason. Right here I have n, m, k in my set of normalizers. And I look at the following functions. I look at the function n, first of all, and then I bring it down to the unit space. So this is the conditional expectation onto the Cartan subalgebra. It's God given to you when you have a Cartan. And then I look at that thing's phase. So this is just the complex number, not the length. It doesn't care about the scaling. And this has to be smooth. This here, if you think of this as the conditional expectation, is entirely functional analytical. It's really no reference anymore to my groupoid. So P, that's my conditional expectation of M. This corresponds to U infinity. Then I have phase of P of, which letters did I pick? NM star, smooth. And for M, I have phase of P of NMK star. And for the last one, I have phase of P of NM. Smooth. And so then you see the dictionary, and you now know where I'm headed, I hope. Comes the definition. If B in A is Cartan, B hat a manifold, and N is subset of the normalizers such that all of the conditions I mentioned over there. So I need it to densely span A. I can't throw away too many things. I need it to intersect with the subalgebra to give me exactly the smooth functions. And I need these conditions here. Maybe I could give them a name. This here is N star, and here we have U star and S star, M star for multiplication, I star for inversion. So if we have N star all the way up to I star, then we call A, B, N smooth Cartan triple. And the theorem then is 3 twists correspond to smooth Cartan triples. And in the last 55 seconds that I have, let me mention that there's obvious routes to follow up now. So the motivation behind this was to try to start building non-commutative differential calculi. So in this case for étale groupoids. So this would be the next route to follow, but we haven't actually started on that yet. So don't ask me too much about that. And thank you.